So, Radhe everyone, and a very good morning to all. Today we are continuing the Road to Expert series again, and in this series, today we are not just solving one code forces problem, but we are solving three CSES problems from uh, searching and sorting section. So, I'll show you guys the problems that we're gonna solve today. That will be towers, traffic lights, and distinct value subarrays. So I just solved them before making this video, and now let's discuss these problems. First of all, I will advise you to pause this video for each problem and then give that a try, right? And then if you are not able to do it, then obviously watch this. Otherwise you can just skip this section and move on to the next one, and then do the same thing again for the next problem. So anyways, let's begin. The first problem, tower, it says you are given n cubes in a certain order and your task is to build towers using them. Whenever two cubes are on top of the other, the upper cube must be smaller than the lower cube. You must process the cubes in the given order. You can always either place the cube on the top of an existing tower or begin a new tower. What is the minimum possible number of towers? So what this problem is saying that we have been given some heights of towers, let's say. So we have been given an array A. This is A1, A2 up to AN. And now this problem is saying that we need to process the towers one by one. So first we'll process this tower, then we'll process this tower, right? So we'll do that until we reach nth tower, right? And for each tower we can see that here we can either place the cube on top of an existing tower or begin a new tower, right? So if let's say we had some tower here, some tower here, and a tower here. So if let's say I've encountered a tower with a height of x, so it is saying that I can only place x where this previous height of the tower is greater than x. So suppose this is a 2x, maybe a 3x, and a x. This is x by 2. Maybe I'm taking any random things. So if it is my x, then this is problem is saying that I can place this tower with height x only above the 3x one, because x is not greater than x and x by 2 is also not greater than x. We can only place tower which is strictly greater than the height, than the current tower's height, right? And now we need to print the minimum number of towers which are required to process all the towers, right? So I'll take one sample and then it will be much more clearer. So let's take this sample 38215. Okay, so first of all, currently we have no towers at all, right? So when we encounter this tower, we will create a tower with height 3. So let's say this is our tower with height 3. Now we encounter this tower, and since 8 is greater than 3 and we do not have anything on which we do not have anything which is greater than 8, because if we need to place 8, we need something bigger than that, right? We need a tower with a height bigger than 8, but 3 is not bigger than 8, so we need to create another tower. So we create another tower of height 8. Then we encounter a 2. So basically 3 is also greater than 2 and 8 is also greater than 2. So we can either place 2 here or place 2 here. So for now I'm placing a 2 here. Then I've encountered a 1. Again we can place 1 here or 1 here. So let's place 1 here. And now I've encountered a 5. But you'll see that 2 is also lesser than 5 and 1 is also lesser than 5. So I would want to create a new tower with height 5. And so for processing this array, we needed to create 3 towers, right? As a matter of fact, if you would have picked this 2 and would have taken this to the first tower, then we could have picked this 5 and placed that on top of it. So what I mean by this is, uh, 1 minute, so I'll just remove this. Okay, so when I encounter a 2 here, right, so if I place a 2 on top of a 3 and then I place a 1 on top of a 2, then I have space left for the 5th one, right? I can pick this 5th tower up and then place it on top of the 8th tower, right? And now we're done in only 2 towers. Previously we were taking 3 towers, but now we can process this array in 2 towers only. So our answer is 2. We need to minimize such the number of towers, right? So how do you think we will solve this? How do you think we can, in each iteration, we can greedily um, take this tower, and then what do you guys think that which one should I, which tower should I choose, and then place this 2 on top of that tower? So I can place 2 on top of 3, and I could also choose 2 and place it on top of 8, right? But for some reason I chose 2 and then I placed it on top of 3, not 8. So why exactly we did that? Or we can imagine something like, if we have a tower with height 3 and if we have a tower with height 8, now if we encounter a tower with height 2, so it doesn't make sense to add that to my tower of height 8, because if we again if we after 2 have something like a 6 maybe, and then a 4 and then a 3, something like that. So if I add this 2 to my 8, right, so if I pick this 2 and add to my 8, then I will not be able to add this 6, right? I will not be able to add this 6 because now the new height will be 2 and new height will be 3. The height of this remains as it is, I'm sorry. So I will not be able to place this bigger element. I will also not able to place this bigger tower. I will also not able to place this one. Otherwise, if we would have done something, if we would have placed this, I'm sorry, if we would have placed this 2 on the top of the 3, then surely we could choose this 6 and place on top of 8. We can choose this 4, place on top of 6. You can choose this 3 to place on top of 4, right? So now we only need 2 towers, right? So I'm saying that for each iteration, for each tower, we can calculate which is the smallest tower which is just greater than that tower. So if you want to place this 2, so I'll see that in my array or in my multi-set or a set, which is the tower which is just greater than this, the smallest tower which is just greater than this. So it is 3 in this case. 3 is just greater than 2. The elements which are greater than 2, the towers which are greater than 2 are 3 and 8, right? So we can either place on top of it or on top of 3, but we will choose the smallest of such cases. So we'll choose this 3 and place this 2 over here, and then we'll move to 6 and do the same. Now my new set becomes 2 and 8, and we'll choose the smallest element which is just greater than 6, which is 8. So we'll pick this 6 and place this on top of 8, and then we'll continue doing this. This will guarantee that for I assign each tower to the or let's think about this way, that this greedy strategy will actually place let's say this 6th tower to the smallest such tower which can accept 6. So if we would have something like a 12 maybe here, so if we in this tower array had an 11 maybe here, then if we place this 6 on the 12 on top of 12, then we will not be able to process this 11, right? So I'm saying for each tower, calculate the smallest such tower which is just greater than this element. So this is 8, and we can place this on top of that tower, and then we can move on and do the same for all such cases, right? And this will always work, because our greedy strategy is thinking the local choice that we make, or the local optimal choice that we make, leads to the global maximum. That's why, or the global final answer. That is why this greedy strategy works. Again, let me repeat. For each tower, when I go to every tower, I will check what is in my already placed towers array, and I'll only keep track of the head tower which is on the top. So 2 is on the top, 6 is on the top, 12 is on the top. I don't care about this 3 and 8, because now this 8 is replaced by 6 and 3 is replaced by 2. So I'm saying whenever I see a new tower, I'll see what are the available towers height, and I will choose a smallest of such element which is just greater than the current tower. So I'll choose a 6 in this case, and I place a 4 here, so that if I encounter some bigger value later, let's say 11 or maybe something else, or 10, then I can reserve the bigger towers to place those bigger elements that will come after these elements, right? So if I had encountered or if maybe I had a 10 and 11 here, or a 11 and a 10, I'm sorry, so we would have reserved this 12th tower to place these bigger elements, right? And so we can keep on doing this. So essentially we just need to find the upper bound of AI. Let me use another pen. So we just need to find the upper bound of AI. And if upper bound doesn't exist, so if we had encountered something like a 13, then we cannot place a 13 anywhere, right? So we'll have to create a new tower. So if this upper bound, let's call this iterator, if this iterator would have been, this is specific to C++ by the way, s.end, right? So that this is checking that if the upper bound for the current tower does not exist, then I would need to increment the towers. Otherwise we can pick the smallest tower which is just greater than the current one, then we can erase this up, and then we can insert the new element AI, and that's it. So this is the code. So I'm using a multiset here to handle multiple towers. So one thing that could happen is I had a 3 and a 5, and then I encountered 2 2s. So I place 1 2 here, and then I place a 1 2 here. So I do not want to, when I encounter a 1, then I do not want to remove all these 2s. I just want to remove one occurrence of 2. So maybe in this case I can choose any of the towers and place one on top of it, and then I can replace only this 2. I don't care about this 2, right? So we'll have to maintain a multi-set, not a set. So I'm now finding the upper bound of AI. If the upper bound doesn't exist, then I'll increment my towers, and then I'll insert the current tower height. Otherwise, if the upper bound exists, then I'll just erase that upper bound and I'll insert my current element, and that's it. I hope you got the solution for this problem. Let's move on to the next one. The second problem is traffic lights. So what this problem says is, there is a street of length x whose positions are numbered from 0 all the way up to x. Initially there are no traffic lights, but n sets of traffic lights are added to the street one after another. So they are adding traffic lights one after another, one by one. Your task is to calculate the length of the longest passage without traffic lights after each addition. So I need to calculate the number of the length of the longest passage without traffic lights after each addition. Okay, the first input contains x, that is the length of the street, and then n, the number of traffic lights, and then we are given these coordinates of the traffic lights, right? So essentially what this problem means is, I'll draw a number line here. Well, let's say this is my number line. This is 0, this is 1, a 2, 3, 4, 5, a 6, a 7, and a 8. So let's take this first sample. I have x equals to 8, so the length of the street is 8, right? And now I have been given coordinates of these traffic lights. Those are 3, 6, 2. Okay, so now I process these traffic lights one by one. So I first go to this first coordinate and I add a traffic light to my third coordinate. So I'll just mark it as green. So I add a traffic light over here, and now I need to calculate the length of the longest path without traffic light. So the length of the longest path without traffic light would be this 3 minus 0 or this 8 minus 3, the maximum of both of them. So in that case it would be 5, right? 8 minus 3 is 5, which is greater than 3 minus 0, 3, right? So we'll print 5 in this case for the first one, then we'll move on to the next one. Now we'll add a traffic light to my 6th position, and now we need to calculate again what is the length of the longest path that does not contain any traffic light. So this is 3 minus 0, maximum of 3 minus 0, 6 minus 3, and then 8 minus 6. So maximum of 3, maximum of 3, 3 minus 0, a 3 again, 6 minus 3, and a 2, 8 minus 6, so a 2, and maximum of these three variables is 3. So I'll take a 3 and I'll move on to the next one. And now I place a traffic light on the second coordinate. Now I check again. The longest passage would be maximum of 2 minus 0, the maximum of 3 minus 2, the maximum of 6 minus 3, the maximum of, and the variable or this one 8 minus 6, which is 2. The maximum is 3, so we'll print a 3 again, and then that's it. This is our final answer. You can check that here. This is we're getting 533, and this is we're getting 533, right? So how do we solve this one? So if you think this problem in the direction of in the number line way, then you can see that if I had some number line like this, okay, I had some number line like this, and I have some, I have these two coordinates, okay, I'll call them L and R, and a traffic light is placed on L also and on R also, right? And if I add a traffic light now in between L and R, so I add a traffic light between L and R, so don't you guys think this was my 0, let's say, and this was my X, I'll call this Y. So don't you guys agree that the answer before this and the answer after this will remain same? That is, if no matter how many coordinates we had here, the traffic light, or here, this one adding Y between L and R will not affect these answers, right? Why will it affect these answers? I'm taking these distances and these outer lines, right? So why doesn't interfere in that, right? I was taking something like this before adding Y, right? But now after adding y, I cannot take this big length, right, from L to R, but I can take these lengths, the ones before L and ones after the R, right? This doesn't change my answer, I'm saying. So adding a y only changes the answer for the element which is just lesser than this and the element which is just greater than y, right? So now this L and R, this was the difference, R minus L. This is broken down into two parts. So now the new distance will be y minus L and then R minus y. R minus y. So this is my new distance, right? So I'm saying nothing matters outside L and the before L, and nothing matters after R. If we maintain a set or a multi-set, right, where we have these distances stored, so this distance, this distance, this distance, this distance, this distance, and this distance, then I could just remove this distance from the multi-set, and I could add or insert y minus L to my multi-set, and then I could insert R minus y to my multi-set, and I could just take the maximum from my multi-set and then print that and then we'll do this for all i's from 0 to n minus 1, right? Also, to find which is the element which is just greater than this and which is the element which is just lesser than this, we'll also maintain a set of the coordinates. First we'll insert a 0 and a x to my set, and then let's say I have inserted all these coordinates. These coordinates I have inserted in my set, right, except y. We are currently processing y. So I have inserted all these coordinates into my set. And if I do a upper bound of y, then I'll get a r, right? I'll get this r. Upper bound does exactly what? It finds the smallest element which is greater than y. This r is the smallest element which is greater than y. So I'll do upper bound to get this r in this set, which stores all these coordinates, right? And to find the smallest L which is just lesser, or the maximum L which is just lesser than this y, so this is the maximum L which is just lesser than this y, I can do a lower bound to find the lower bound exactly does what? Lower bound exactly does what? Finds the element which are greater than equals to current. So if y existed in my set, but it current element, so when I'm processing y, so currently y does not exist in this set of mine, right? So if I'm processing y, only r and l and these other coordinates, this x1, x2, x3, x4, and this x5 and then x6, these exist in my set. And this is also exist. So this is x4, and then you can shift this y1, x5, x6, and x7, right? So I'm saying these already exist in my set. I could just run a upper bound to find this x5, and then I could run a lower bound, and if I do a lower bound of y in my set, I'll also get this x5, because this is greater than equals to y. And then I could do a lower bound -1 to find the greatest element which is just lesser than y, because lower bound exactly does is what? It finds the smallest element, or I'm sorry, it finds the greatest element which is just or finds the element which is greater than equals to the current element. So if even though we are guaranteed here that each set of traffic lights would be distinct, still if we would have if y would have existed before processing y, let's say we had two y's, then in this lower bound we would have gotten this as the answer, and I would just had subtracted just 1 to get this x4, right? But these coordinates cannot repeat, so I'll get this x5 as my lower bound, this x5, right? And then I'll subtract 1, so I'll get this x4 as my lower bound, right? So this is my L and this is my R, and now I can remove this r minus L from a multiset, this distance of r minus L from a multiset, and then I could insert this y minus L and this r minus y to my multiset, and then I'll just take the maximum from my multiset to print the answer for this particular iteration. And then again I will insert, I'll take this element and then insert into my this set, right? So that's it. We'll do this for all the coordinates and we'll get our answer. The main thing for solving this problem that was necessary was that if I add any particular coordinate to my number line, so if I add some coordinate to my number line, the only value that gets affected are the one just left to it and then one just right to it, because this eventually this distance now becomes r minus l would now becomes y minus l and r minus y. This distance eventually breaks down into two parts. So that is what I'm doing. I'm creating a multi-set to store these distances, and I'm creating a set to store these coordinates. To find the coordinate which is to find r, I'll just do a upper bound. For finding this l, I'll do a lower bound -1, and then I'll erase this from a multi-set. I'll add this to my multi-set and add this to my multi-set, and then I'll take the maximum from a multi-set, right? So the multi-set would store length of interval, length of valid interval, I would say, with no traffic lights, length of valid interval, and I'll take the maximum from a multi-set. We can get that in order of, I think it was 1 only, and then I'll insert this current element y to my set. Set will store my coordinates of traffic lights. And that's about it. For each iteration I can just pick the maximum element from a multiset, and then that's it. So I'm taking this array as the input, right? I'm creating a set here. I'm inserting 0 and x to my set because these are the boundary element. Now I'm creating intervals, multiset called intervals, and then I'm doing a upper bound here. I'm doing a lower bound here, and then I'm doing minus to the lower bound, since we need to find the left element, right? Now we insert the current element to my set. We can also do this at the last, it doesn't matter. Now we erase ITR minus ITL. So ITR would give me the RH element minus the LS element that we saw here. We are actually removing this R minus L from a multiset, right? And then I'm inserting this y minus L, that is this one, y minus L, the current element. This is y, and then this is L, and R minus y. So this is R, the right coordinate, and this is y. And then I'm inserting this to my intervals multiset, and then I'm just printing the biggest element which is present, or the biggest valid interval which is present in the multiset, and that's it. This is probably it. I hope you got the approach. I would want you guys to digest it a little bit, spend some time trying this problem on your own, and then you'll get the solution very easily, right? So yeah, let's move on to the next problem. This is distinct value subarrays. So given an array of n integers, count the number of subarrays where each element is distinct. Okay, so we need to count the subarrays where each element is distinct. So if I had an array like a 1 2 3 4, so all elements are distinct, so I could create a subarray as 1 1 2 1 3 1 3 1 2 3 4, then 2 2 3 2 3 4, then a 3 3 4 and a 4. So this is 4 plus 3 plus 2 plus 1. So this is nothing but n into n plus 1 by 2 formula. So I'm saying if this is the length of my valid subarray, so if this is the length, so I'm doing a length into length plus 1 by 2, and this will generate all the valid subarrays, right? And then we can process it as, if we would have had something like 1 2 3 4 and then a 1 again, maybe something like 5 6, right? So I'm saying I could pick this subarray, right? If I take this subarray and then the length is 4 here, so I could do a 4 into 5 by 2, so this will be 10. So I could generate 10 subarrays from here. Now since this one is repeating, I cannot take this further, right? So I'll have to take something like this, and then we can generate all the subarrays from here to here as well. So the length of this subarray is 1 2 3 6. So this is 6 into 7 by 2, which is length into length plus by 1 by 2, so this is 21. So we'll just add these values, but the one thing is, if you see carefully, this 2 3 4 is common in both the intervals. So we would be generating subarrays consisting of this 2 3 4 for the first one also and for the second one also. So we would be overcounting this subarray, right? So we need to subtract that. Okay, so we will need to subtract this length. So this length is 3, so we'll 3 into 4 by 2, this is what, 6. So we'll need to subtract a 6 from the total answer. So 10 plus 21 minus 6, this is the final answer for this test case. Now how exactly to do it? If you think about this problem in a 2-pointer way, so I have my array as 1 2 3 4 1 5 6. So I keep expanding my subarray as long as I do not encounter an element twice. So as soon as I encounter an element twice, I can take the length minus 1. So if this is the length, I can take length minus 1 till here, right? And then I could generate the subarray, or I could generate all the subarrays by doing length into length plus 1 by 2, right? Then you saw that we generated all the subarrays from 1 to 4, and now we need to move on to the next subarray. So I'll decrease this L pointer. So this was my L, and this was my R. So I'll decrease this or increase this L, and now my 1 is occurring only once. So I could take this R and keep on increasing as soon as I do not encounter the same element twice. So in this subarray, we do not encounter any element which is present twice. So we are taking this subarray. Now we can take the length of this subarray, or this loop would run to the end of the loop. So right. So instead of taking this, we will take minus 1, length minus 1, and then I'll generate all the subarrays by doing length into length plus 1 by 2. So this is 1 2 3 5 6 elements are present here, right? So I'm doing 6 into 7 by 2, which is 21. But I also have some elements which are occurring again. So this is 2 3 4. So I need to subtract that. So how do I find which elements I need to subtract, or the length of the total subarray that we need to subtract? So we need to subtract this from the answer, right? We need to subtract this 2 3 4 from the answer. So for subtracting that 2 3 4, I'll see when I was at this, when my L was here and my R was here, I stopped my R because I had encountered a same element again. Okay, so I stopped my R. Now I need to take this length. So I'm saying whichever elements are present between these two same elements. So one was same, and this one was occurring twice, right? So the 3 elements are present between ones, right? So I'll update my extra to this 3, and then when I process the next subarray, which would be this one, then I will decrease this extra into extra plus 1 by 2. So extra, let me just use e plus 1 by 2. I'll decrease this because this is occurring twice. And why exactly we are doing this, I'll show you guys. We are doing it because we know that when we had encountered the same element twice, which is 1 and a 1, so all the elements before it are already taken, right? Are already taken. If we would have something like a 10, a 12, 13, so this would have been my subarray. Okay, so now when I try to take the next subarray, it will start from this 2 and will go up to the end, right? It will not start before this 1. It will not be something. Otherwise, in this second subarray also we would have 2 occurrences of 1. That is right, this and this. So in the next subarray we will not have 2 occurrences of 1. We can only have a one occurrence of every element, right? So if I process this subarray and then we have encountered 1 is occurring twice, then we need to eliminate this part, right? So we'll begin my subarray from here and go up to the end, right? So basically what I'm saying, to find the number of I can just find the number of elements between the two same coordinates, right? We can create a map, 2 maps actually, one to store the frequency and the second one to store the last occurrence of that particular element. So if I'm following a 0 based indexing, that would be 0 1 2 3 4 5 6 7 8, something like that. And now the last occurrence of 1 would be 3. When I do a 7 minus 3 minus 1, so 7 minus 3 is 4, minus 1 is 3, so I'll get the number of elements which will be occurring twice. So I can update my extra to these extra elements, and then when I'm processing the next iteration, that is the next subarray, that is this subarray, then I will subtract this 2 3 4 of these extra elements by doing a e into e plus 1 by 2. I'll subtract that from my final answer, right? And this is about it for the problem. This is just it. This is the code for this problem. I have 2 pointers, 2 maps, one storing frequency and one storing the previous occurrence. This last actually stores these extra elements, so I've named it as last. This total is the total number of subarrays. Okay, so forget this boolean for now. I'm incrementing the frequency of the current element. If the frequency of the current element becomes greater than 1 or equals to 2, then I could take my length, since I was following a 0 based indexing. So if I had encountered something like 1 2 3 4 and a 1, so if this was 0 based indexing, then 4 minus 0 will actually give me this length, right? So I do not need to add an plus 1 to it. So I can do j minus I to get the length, then I could add length into length plus 1 to my total. I could subtract last into last plus 1 by 2. This is extra into extra plus 1 by 2 from my total, right? Which was, it was initially 0 anyways, right? And then I could update the last to be j minus previous of aj minus 1. So this is, if this would have been j, right? Since we encountered 1 twice, this would have been my j and this would have been my last of j or the last of aj. So when I subtract this 7 from 3, I'll get a 4, and when I subtract a 1 from that 4, so this is essentially just j minus last of aj, and I could do a minus 1 to this to get the number of elements between these two consecutive or two same elements. We can get how many elements are present between two same elements. So I'll update my last to be at this thing, and then I'll run a loop. So as long as this frequency of aj is 1, so I need to eliminate this subarray completely, right? So if my L was here, I'll keep increasing my L and decreasing the frequency of these elements as long as the frequency of the current element does not become 1. So this is 2 for now. This is again 2 because I'm decreasing the frequency of 12. This is again 2. Now this when I remove the frequency of this one, this becomes 1. And now I can take my subarray from this part, from 2, and then I can keep expanding as soon as I do not encounter a same element twice or I finish this array completely. So I'm at last also checking, but we'll come to it. I'm updating my previous also, and I'm incrementing j in each iteration also. Okay, Also, I'm checking if the last element would have been same element, let's say 1 2 3 4 1. So if my last element would have been the same element, or the element which is occurring twice, then I do not want to process this last subarray. Otherwise, if it would have been something like 7 8 9, then I would want to process this subarray, right? Because this is not occurring twice. As we can see in this code, we are performing this operation only when this frequency is twice. So in this case, the frequency is not twice, so we'll need to actually perform this operation over here. So that is essentially what I'm checking, that if j equals equal to -1, so the last element is occurring twice, then I can just forget about this thing, because then I would have already ran this operation, right? I would have already taken into account that particular subarray, so I could uh, set this p as true, right? Otherwise, if p is not true, that means I need to handle this particular subarray. So I'll do that, exactly the same thing that I was doing here. Otherwise, I need to add 1 to my total. So if it would have been something like 1 2 3 4 and a 1, so I had taken everything to my answer, but this thing, exact thing, this one, only one element is remaining, right? I had taken all the subarrays 1 2 1 1 1 2 1 3 1 4, and then 2 2 3 2 4 2 3 4, and then I'm sorry, a 3 and a 3 4. The only thing that is remaining is just taking this one separately, and since we didn't do it here, we didn't taken this one into account in the last iteration, so I'll add this. I'll just increment my total by 1 to handle this case, and then I'll just print my total. That's it. This is the total, this is the complete code for this problem, right? And that's it. We were able to solve 3 problems. These were not very hard, not very easy problems, but I hope you enjoyed it. I hope you got it. This is my Road to Expert series. We're containing this. I hope I'll continue this every day, but yeah, let's hope for the best. I'll see you guys in the next one. Also, today I was shooting a blog. I'm sorry, I was shooting a vlog, and then I was just recording my daily routine. So yeah, I think that would come in night. So stay tuned. Yeah, there I hope to bring a lot of content, a lot of things about my life to document it. But if you're watching, then please let me know and stay tuned. Thank you for watching. Radhe Radhe.